Well, my name's Chris Brogel, and I'm the Global Vice President of Safety for Ross. And I've been in the automation industry 41 years now, and 30 of that in the area of safety. And so during my background, I owned my own automation company building custom equipment, and a lot of it had hydraulics, pneumatics, and of course electrical. And as John was saying this morning in the kickoff discussion, it all works together today. And so what we're going to do, what the agenda is going to be, is I want to talk about the current conditions in the industry, just one or two slides on standards, because the safety standards, there's been quite a few updates over the last few years that are changing things, and there's been a lot of influence from the US standards on the European standards. And then talk a little about the standard structure, and then discuss a topic called standardized safety approaches. And what I mean by that is companies that have a standardized approach that includes doing risk assessments, developing functional specifications. Those functional specifications then drive the design, then doing things called design verification calculations, and then validation after implementation gives you kind of a cradle to grave process. So we're going to talk about that as we go through, and then we're going to spend a little bit of time on what's the difference between standard valves and safety valves, and how they get implemented. And what I'm going to show you is a lot of times people are using standard valves and putting downstream sensors and thinking they're just as safe as a safety valve, and they just don't understand. So we're going to go through those topics. So the current conditions right now in the industry is people are confused about what standard to follow. If you go and look up standards, there's thousands of standards, and there's A, B, and C type standards. A standards are your basic risk assessment standards. Your B standards are your technology standards, and then there's C type standards that are for machine specific standards. And then you've got this other thing of machinery safety and process safety. Process safety is a whole different animal than machine safety, and there is a whole lot of valves being used in that petrochemical industry, and it's just as unsafe or more unsafe than machine safety. You think about machine safety, you're usually protecting one or two people. Process safety, you're oftentimes protecting the community because you don't want a hazardous release, but they're using valves, hydraulic valves and pneumatic valves all the time. And then you got what I call the hybrid industry, which is even more confusing. Think about a whiskey manufacturer. They have a whole process side, and guess what? That liquid that they're manufacturing is highly flammable. So you have a process side. Then you get over on the other side, you've got all the packaging and bottling and all that stuff, which is machine safety. So I call these hybrid type customers. And when we look at those industries, they have different ways of doing things. So the biggest difference between what I call general manufacturing and machine safety is you try to prevent access to the hazards. And what you do is you stop the process and you shut it down and you keep it from moving. And then in the event of a power down or a shut off of the system, that's what it tries to do, is take it to that safe off state. Well, in process side, shutting things down can cause a very unwanted situation, meaning chemical, when you're mixing chemicals, those chemicals, if you stop it in the wrong part of the process, you just create an explosion. Or you may have a product that sets up in the lines, and like one of my customers, their mixing process, if you do it at the wrong time, you basically get concrete in the lines. The only way to fix it is tear all the piping down, put new pipes up. So process safety says keep it running, but keep it under control. Machine safety says shut it down. So it's a different way of doing things, and it's totally different calculations. And when you look at machine safety says the most effective way is to eliminate the risk. And a lot of time that's requiring redesign. If you can design the hazard out, that's great. That's elimination. or you do substitution where you may automate that loading to keep someone from having to be interacting with that dangerous part of the machine. And if you can't do that, then you get into what we call engineering controls, and that's where safeguarding comes into play. And if you can't safeguard it, then you get into administrative controls, maybe giving people gloves or giving them PPE or tools to work with. And so that approach is a little bit different than the process industry. Process is totally opposite. It starts at the bottom with what they call basic process control. So this might be a PLC that's running a tank or running some fill systems or some mixing systems. And above the basic process control system, you've got your alarms and intervention. If that process starts to get out of range or out of acceptable limits, you sound an alarm, and then the operator is supposed to go take care of that alarm. If that alarm doesn't take care of the situation, you have something called a safety instrumented system above there. And that's where you get into safety valves and that are being controlled by some like overpressure, over temperature type applications. And then above and beyond that, if the SIS system doesn't control it, you have to contain it. So it might be like a flare. You ever been by a factory and seen a flare? It's burning off unwanted gas is what it's doing. Or you go to a oil mixing facility, they've got containment dikes around it so that if there is a spill, it doesn't get outside the facility. And then they have a community action or a plant action plan and a community action plan. So the whole approach is totally different. It's all about elimination and removal of hazards and machine safety. It's about controlling the hazards and process safety. Guess what? They may use the same exact valves. And so when you start looking at that hybrid type industry, and in this case I had whiskey, but it could be the paper industry because you have the whole, what I call the pulp side, all of that pulping, basically getting the pulp material out of the wood, that is a whole process side. That material, that pulp, then goes in to make the paper. You get into making the paper, you've got rolling lines and everything else. And in this case, on the whiskey side, if you look, you have a depalletizer that basically unstacks the bottles, puts the bottles on a conveyor. It goes through a rinsing station that cleans them. That may even have some hybrid because you may have some cleaning fluids that go into those bottles, like alcohol or something like that goes in, and I'm talking like an isopropyl alcohol to clean the bottle. Then you got air blow that blows it off. Then it gets into the filler, the capper, the labeler. Sometimes there's pasteurization that happens, so you're doing temperature control. And then you get into the labelers, inspection, case packers, and palletizers. It's a lot of moving pieces that are machine safety related. And a lot of places that we see hydraulics being used in this process is on that depalletizer and the palletizer because it's lifting some pretty heavy loads. And so we get into kind of a mix when we get in those hybrid industries. And the way the standards are structured is in what they call A, B, and C type standards. So your A standards are what they call general safety standards or basic standards. And that deals with risk assessment and basic risk reduction. You get into the B type standards. These are more generic for technologies. Like there's a standard for hydraulics called the ISO 4413, one for pneumatics, ISO 4414, ISO 13849, which is for machine safety design. You get into a 61800. This deals with things like drive systems. 61508 deals with electrical and electronic circuit boards. So these B standards are more what I call product or application standards. You get into C standards, they're for specific machines. Like, for example, there's a ANSI RA standard. There is the ISO 10218, which is the robotic standard. You've got press standards, material handling standards, even chopper standards. And so there are C-type standards, which are specific for machine types. And when we start looking at those A-type standards, there's two different ones that are used. ISO 12100 is for the machine safety side. And what it says in that standard is it provides a comprehensive framework for the safe design of machinery. When you start looking at IEC 61882, it's a standard that outlines requirements for HAZOP. So instead of risk assessment, they call it hazardous operations. So there's two different ways to do assessment depending on which type of plant you have and what kind of facility and processes you have. A big part of what is in the hydraulic world is here, but when you start looking at oil and gas, they're using hydraulic valves to open some of those big gate valves that they're using in the industry. So it kind of falls on both sides, and depending on what type of manufacturing you're doing. The ISO 12100 standard basically says that it defines the requirements for risk assessment and risk reduction. And it says right here, you need to determine the limits of the machine, okay? Is this machine one station or is it a line? And then what are the operating speeds? What are the voltage, the pressures, things like that that the line's running at? That's determining the limits. Then you have to identify hazards associated with running that line. Once you've identified those hazards, you need to estimate the risk. And there's a bunch of risk estimation methods out there. I'll show you one or two here in just a minute. And then you need to evaluate and see if that risk is acceptable. If it's not acceptable, you get into the bottom half, which deals with risk reduction. And so you remember me talking about just a minute ago about the first thing, can it be removed or eliminated? That's the first hierarchy. If it can't, can it be guarded? If it can't be guarded, what type of safety control solutions can we put in place? And those control solutions might be a door switch, or it might be a light curtain. Once you break that light curtain or that door switch, it signals your valves to operate and take the machine to a safe condition. And then if you can't put safety protective devices in place, well, that's where you get into procedures, PPE, things like that. So that is the risk assessment and risk reduction process per ISO 12100. When you get into IEC 61882, you have to go in and look at what part of the system you want to deal with. Are you dealing with one function? Are you dealing with multiple functions? And you have to identify what the relevant elements are. So what are the things that could cause the hazards? And where are those hazards coming from? You then need to evaluate if the current situation on the machine is adequate or not. And if it's not, you need to determine the control measures you're going to put in place. It's a very similar process. It's just we're looking at different things. And these B-type standards tell us how to use specific devices. And there's a B1 and a B2 standard. The B2 standard tells us how to do the design. So in machine safety, we're using something called categories. You'll have category B to up to category 4 type valves. You start looking over in the process side, in the safety instrumented systems, they're using SIL levels. And so they're using more hardware fault tolerance type situations versus category. So they do things just a little bit differently. Process is similar. And so a lot of people ask me, okay, what standards should I be following? It depends where you're at. If you're in the industrial sector, the primary standard for machine safety is ISO 13849 that drives the design requirements. Process safety falls under the energy sector under 61508 called 61511. And that basically is what drives the design for process safety. So there's two different figures. ISO 13849 uses something called performance levels. IEC 61511 uses SIL levels. So safety integrity levels and performance levels are the two terms that I'll use through the rest of the presentation. When I look at ISO 13849, it says that it provides safety requirements and guidance on the principles for design and integration of safety-related parts of the control system, and that is to include electrical, hydraulic, pneumatic, and mechanical. So you can't ignore it anymore. In 1996, when this standard was written, there was no one really addressing fluid power. In the 2006 version of ISO 13849, it added the requirements for electrical or for pneumatic and hydraulic. Okay. And this is for what they call high demand systems. What we mean high demand systems, it's got to be continuously ready to trigger. Meaning, I open that door, I'm going to dump that valve, or I'm going to reverse the direction of travel of that cylinder, whatever the safety function might be. That's called high demand systems. When you get into process safety, it's low demand, because you're not shutting that thing down, but maybe once a year or once every 3 months. It's a different approach. And so, but keep in mind that pneumatics and hydraulics is now part of that system. And when we look at 61511, they use things called an SIS, Safety Instrumented System. And like I said, the way they do things is they develop and do they call it HAZOP in their world, but it's basically a risk assessment. Then they determine what safety functions go into those different protective layers. Remember I showed you there was a basic process control, advanced process control, safety instrumented system. So that's where you determine the safety layers that need to be implemented. Then you develop your requirement spec. Very similar to machine safety. You do a risk assessment, you jump to the design spec, you get into engineering, installation, commissioning, and validation. But on the process side, they have a whole lot more information about operation and maintenance, modification, and decommissioning of the system. So the process side goes a whole lot further, because think about it. Machine safety, you're protecting one person. Process safety, you're protecting the community and the environment. So it's got a little more meat on the bone there. And that's why it's important for companies to have standards. This one company here, Chartered Next Generation, is a customer I'm working with in the US. And I asked them, I said, what kind of safety standard do you have? And they pulled out one page. It said, all machines will be safe. The machine builder is responsible for giving me safe machines. I said, okay, explain safe to me. What's your definition of safe? And what their definition of safe is probably going to be different than yours. And so what we did is we helped them actually write a safety specification that basically outlined what the scope of it was. It was for new machinery, existing machinery, and machinery that's going to be modified by either CNG or its integrators or machine builders, what the responsibilities were, what the standards were to be followed. So there was 3 pages of standards that they added to this based on the type of equipment that they had. And then that there's a requirement for doing risk assessment and risk reduction. I just gave you kind of the introductory of each of those. Each of those were about a page. And so their standard ended up being about 45 pages. Now, I went to another company that handed me a 450-page, here's our safety specification. Guess what? That is as useless as that one page, because nobody's going to read that 450 pages. And so having a specification that defines the requirements is best practice in the industry. And to me, it's almost impossible to succeed in safety without having a safety plan and a specification. It's like shooting before you aim. If you don't have a plan that directs your target where you want to be, you're going to fail. And so what Ross has done is we implemented what we call a 7-step to success program. And it starts off with determining what your safety program is going to be, auditing your plants and determining where you have insufficiencies. And when you identify those insufficiencies, then you get into machine risk assessments. Those risk assessments drive update plans, which drive the modifications. After they've been modified, they have to be validated. And guess what? You got to train your people how to run those machines afterwards. And that's the same whether it's machine safety or process safety. And so we've been helping a lot of companies, and you might recognize a few of these: DuPont, Bridgestone, Goodyear, 3M, helping them with their safety programs. And once we help them with the safety programs, some of them, when we're discussing, we ask, what kind of lockout program do you have? One that we've been working with for a couple of years, Smurfit Kappa, they didn't even have a defined lockout program. So we actually came in and wrote their safety lockout program for them. And it started off with doing a machine inventory, developing specific procedures for handling hazardous energies, and that's hydraulics, pneumatics, electrical. And a lot of people think, I just shut that ball valve off or I turn the pump off, I'm at zero energy. Problem with that, a lot of your pumps will have check valves right in the pump. As soon as you shut the pump off, check valve closes, now you got stored energy. And you've also got this thing called gravity. Sometimes it's pushing down on a load. You turn the hydraulics off, you turn the air off, things might fall. So you have to think about things like that. Then that drives those specific procedures for handling those energies. Then you get into training your employees and contractors and doing periodic inspections of the program. And then part of the discussion we have is, what are your KPIs? What are your goals that you want to implement? Have you been tracking near misses and accidents? Where do you lie right now? And putting an agreed upon scorecard so that we can start tracking what's happening in the facility. And so we do that usually up front to help companies create a framework for success. The next thing we do is we go in and we work with the customer depending on what their safety requirements are, whether it's process or machine. And we do a thing called a conformity audit. And we basically identify conforming and non-conforming machines. And we use a weighting system based on the input. I know this is an eye chart, but each one of these has got a drop-down list with questions that we answer. And basically the output of that is priority 1, priority 2, priority 3, and potentially compliant machines. So they know where they need to put their next investment. And so an example I'll use, one of our customers came to us and he said, I've got 37,000 machines across 152 plants, and I have no idea where I'm at. And if I try to do risk assessments, they're 5,000 to 10,000 a piece. There's no way I can afford to do it. We went in and did conformity audits, and myself and another guy went and did one plant that had 752 machines in 4 days. So it's a very quick look at the machines to identify potentially compliant machines and non-compliant machines, and it helps to prioritize their next steps. And so what this particular customer did is they identified their priority 1 machines they're doing this year, 2025. Priority 2's 2026. Priority 3's 2027. So they put a 3-year program together to address all risk in their factories. And we call that a conformity audit process. And this is an example of one of those reports. And this happens to be at a paper facility. As you can see, the big paper rolls here. And when we analyze the plant, you notice there's not a lot of green over here. There's a few green machines here, but they had a lot of priority 1s in red, a lot of priority 2s. So we helped them put together a framework across all 152 facilities. And so this kind of helped drive the risk assessment process. And for them, we identified across these lines, because they had a lot of common equipment, 9 main machine, well, not 9, 8 different machine types, and that represented the biggest risk. And so on those 8 machines, we went in and did risk assessments. And the way we do risk assessments is we do a task and hazard based assessment. This is only 1 page, and this is just one job task. There might be 30 job tasks people are doing. But what we do is we look at the job task and we identify what hazards are caused by doing that job task. Then we evaluate those based on severity, frequency of exposure, and possibility of avoidance in order to determine what we call the inherent risk level of the machine. That inherent risk level then tells us how we need to design the machine. In this case, we had some nice red stuff here, high. And that tells me that I need to design my system to meet performance level D and category 3 structure. What that means, it's got to be a dual channel safety valve. And it's got to have the right level of diagnostics to be able to meet performance level D. So that's the way the risk assessment process works. Then what you do is you do brainstorming for risk reduction measures. Once you've identified those risk reduction measures, you go back and look at severity and frequency and the possibility of avoidance, and you should be seeing it drop. So we dropped to low and negligible. So we saw a decrease in the risk on the machine. This is the way you document a risk assessment in the machine safety world. Process safety is a little different. Process safety looks at what is the person doing. In this case, dosing using 100% SO2 liquid. So adding some liquid to the process. What is the health risk? And then what is the severity? What's the likelihood that they would actually be exposed to that unsafe situation? And then it gives you a risk level. That risk level then lines up with something called SIL levels, safety integrity level. So it's a little bit different. The machine safety, like I said, is using performance levels. Process safety is using SIL levels. It's still the same type of assessment, but we're looking at things a little differently. And then those risk assessments and those HAZOPs should drive what we call a machine risk reduction plan. And this one is a machine safety risk reduction plan. And it showed where we needed to put guarding, where the area scanner was going to be configured to prevent access, and then what we needed to do to control both electrical energy, but also pneumatics and hydraulics. And so this is where your system kind of starts tying together those electrical devices to the output devices. And in the world of process, they do things a little bit differently. So if you look here, they have 3 test sensors in the field. These test sensors are going to a logic solver. That logic solver is then driving a valve, and that valve could be pneumatic or hydraulic, depending on what they're doing. But they use like a voting system. So in machine safety, it's usually dual channel systems. If either channel goes off, you shut the machine down. Process world, you want to keep the line running. So what they do is they use a voting system. Okay, I had 1 sensor that went out. Well, 2 sensors are telling me this. I'm going to go with the majority rule, and I'll keep it running, but I'll sound an alarm and say, hey, that sensor's bad. You need to get out there and fix that sensor. So keep in mind, process wants to keep it going. Machine safety wants to shut it down. So any fault in a machine safety system would drive a take it down signal. If one fails here, it gives you an alarm, but the other 2 keep control to keep the process running. So it's a totally different approach. But when we start looking at it, it's all about input, logic, output. And in this case, they've got 3 sensors. In the machine safety side, a lot of times you got a single sensor, but it's dual channel. And that dual channel is going to the safety logic device, that input signal, controlling a redundant safety output device. That safety output device also has feedback that tells us that it actually achieved its safe state. You look at the process world, you may have, like I said, those 3 sensors going to a processor, a 3-channel processor that's controlling redundant outputs that keep the process running. Those are driven by safety type valves that have monitoring on those to tell that the system is either open or closed, that it's doing its function. So it's the same kind of thing, input, logic, output. And when we start looking at machine safety, the different valves do specific functions. And what I'm getting at, a lockout valve, of course, isolates and dissipates energy. Safe exhaust valve automatically by the control system dumps the air. Safe dual pressure select would switch between high and low pressure. Anyone ever heard the term collaborative robots? Those collaborative robots, what they do is they slow the robot down and they limit the torque so that it won't kill someone. Well, the problem is you got tooling on the end. That tooling's at full pressure. It'll still crush your hand right off. We're doing what we call pressure select, and we're switching between high and low pressure, just like they're doing with the robot. When someone goes into the area where the robot is, now it's at a lower pressure that wouldn't create an injury. Still does its job function, it's just doing it differently. Then sometimes you've got an unsafe situation that you want to get that hazard away from the operator. So that's where we would use the safe return valve. You stop the direction of the actuator, send it in the opposite direction. Then you've got things called safe load holding. Sometimes you want to stop and hold that load. You don't want it to move anymore, so you get into load holding. Then you get to the hydraulic world. We've got equivalents, but they use different terms. We still call it lockout in the hydraulic world. But then instead of safe exhaust, we call it block and bleed. You block the supply and you bleed the residual back to tank. We also have different block and hold valves. These are inline hold valves. These are at the stack or at the manifold, and that's used for stopping and holding actuators. So this is stuff that can be done in the machine safety world, but machine safety valves have defined functions that execute specific things like stopping, holding, returning, whatever. You start getting in and looking at the terms that are used in the industry. Everybody knows the electrical terms like safe stopping, energy dissipation, safe speed control, safe direction. Well, we have similar terms in the fluid power world. We call it lockout and energy isolation. We call it safe exhaust for pneumatic, safe stopping or safe control, safe speed control, safe return, safe load holding. We can do the same things that people can do electrically in the fluid power world. And so those technologies are here today and they're being used and applied. And people ask me, okay, what do you mean you're talking about safety valves and standard valves? Well, if it is a standard valve and it has no monitoring on it and there's no safety data, meaning the manufacturers of safety products have to publish safety data. What's the failure rate of this valve? So we put our valves on test and we run them until 10% of the products fail dangerously. And that's what we call a B10D value. So most of your safety companies will have a listed value of failure rate. If there's no failure rate and there's no monitoring, you're category B, you're at the lowest level. If you have one that has no monitoring, but it has safety data, like B10 or B10D, if you have safety data, that is a Cat 1 product. You still have no monitoring here. When you get to category 2, whoop, hit the wrong button. Category 2 is still a single valve, but now it has monitoring, plus it has the safety data. And so that's a Cat 2 single channel valve with monitoring. When you get into Cat 3 and Cat 4, basically it's redundant valves with redundant switches monitoring each valve. And so these are the kind of valves that Ross specializes in, is those Cat 3 and Cat 4 valves. We also make the Cat 2, Cat B and Cat 1, but in the safety area, Cat 2, Cat 3, and Cat 4 is all that we consider safety valves. And then the process world is different. You may have some of the same functions like doing a safe return or a safe exhaust or a safe load hold, but the products are rated differently. And if you look here, these will have ATEX ratings or class and div ratings. So these are explosion proof ratings. They also will have ratings like, for example, 1 out of 2, 2 out of 2. So that's where we're using that voting system, because structures are different for process valves. And then we have different coil types, and those coil types either limit energy or they seal the coil, one or the other, depending on which coil it is. But these are explosion proof type coils. And so those are used a lot in the process industry. And what's used here in Europe is ATEX ratings. And so ATEX ratings basically use the first digits here to tell what type of valve it is. So CE just means that this complies to the CE directive in Europe. You've got a UKCA now, so it would be a UKCA if it was one that you were using here. It also has the number of the notifying body, this 4-digit code. Then you see EX, that machine means it is good for explosive atmospheres. Then the next one, it tells you the type or group it's in. If you look, group 1 is for mines and below ground. Group 2 is for all other equipment above ground. And then you get on past that into your equipment categories. M1 and M2 are mining. And 1, 2, and 3 are non-mining equipment. And then the last digit here, G is for gas, D is for dust. So depending on what you have in your environment, this tells you which valve you need to use. So the process world is different because they're looking at blowing stuff up, whereas the machine safety world's just shut it down. So thinking about things, we were talking earlier about engine test stands out there. You got gasoline coming into those. So it's not just machine safety. You got moving parts and things like that you got to worry about. You got explosive gases. And guess what? A lot of those vehicle testing stands, they have CO2 gas to put the fire out if a fire happened with that gas. Well, guess what? CO2 is not real healthy for you. So you have to use proper valves to control those. Okay. And then there's one thing that's common to both the process industry and machine industry, and it's lockout. And I'm going to tell you this right now. 90% of the lockout I see in industry is wrong. And the reason, it says that the lockout valve should be well marked or distinct from other manual valves. Have you ever gone up to a machine and seen 20 ball valves and none of them's labeled telling you this is the lockout valve? Kind of hard to decide. So it either has to have a proper label on it or it's got to be unique in appearance. So it's easy to identify. The other thing is it says there has to be a full diameter exhaust. Most people are using ball valves for lockouts. Ball valves do not have a full diameter exhaust. The other thing should only be able to be locked in an off position. The ball valve, you can take the nut off of, turn the handle around, and you can actually lock it in an on position. That's a problem with it. The other thing is they've got to be tamper resistant. Anyone ever seen the handle come off of a ball valve? Yep, it's because somebody's tampered with it. The other thing is there has to be a way to verify that pressure has been released. Ball valves don't do that. And 90% of the applications I see in the industry are using ball valves. Not correct. So that ball valve should be the first thing you see. Just follow your incoming air line. That's what you should see first is your lockout valve. Chris and I were just looking at some circuits yesterday. They had a ball valve up here and a lockout valve here. Another one, they had their dump valve in front of the lockout valve. You're going to have to service it. The lockout valve should be the first thing that isolates energy so you can do those repairs. And we do have not only pneumatic lockout, we have hydraulic lockout. And this hydraulic lockout valve is lockable only in an off position. And this one is a four-way type valve. Any of you ever shut off a ball valve or a valve in your system and damage your hydraulic pump? Especially if you got variable displacement pumps with swash plates, you will damage your pump if you deadhead it. Our valve is a single handle. You rotate it to the off position. The pump flow comes in on the P port, goes out on the T2 port back to tank. What's on the machine side goes through the T1 port back to tank. There's two different return lines so you don't deadhead your pump. And it also has a pressure gauge to tell you when you reach zero energy at the machine. And it's a single handle. And if you read even the ISO 14118 standard, it says a single deliberate action for lockout. Most of your ball valves out there have one handle for blocking the supply and one for bleeding it. It's not compliant. It doesn't meet the requirements. And then there's different dump valves. And on the pneumatic side, we call it safe exhaust. We call it block and bleed on the other side. And the block and bleed valves basically block supply pressure and do the same thing. They redundantly bleed back to tank. And we are working on a stackable version of that should be out in early next year that goes right on the manifold. And so these are what we're doing. And if we look at the B10D values, up to 25 million cycles. So very high reliability. And they have third-party certifications. Then we have what we call the stop and hold valves. And in the hydraulic world, we call it stop and block valves. They block the lines, prevent things from moving. And these we have all the way from Cat 2 through Cat 4. And again, third-party certified valves. And then we have other functions which because of time, I'm going to have to move through them pretty quickly. There's the safe return valve, which basically stops an actuator, reverses it to the correct direction. The pressure select, and then you've got all of your different valves for process as well. And so in the process side, sometimes people don't want to shut their process down, so they want to keep it running. These have hot swappable coils, hot swappable valves. So if your process is running, you don't want to shut it down, you basically take the end cap off, you rotate a button inside, which blocks the port here. Then you can change your valve out, put it right back on, release that, put the cover back on, and you're back running in full order. So you're not shutting your process down at all. It's a hot swappable valve. And just keep in mind, all of your safety solutions are made up of input, logic, and output. And when we look at machine safety, performance levels are made up of the category, they're made up of reliability, and they're made up of diagnostic coverage. And that's what makes a performance level. And so what that means is I have to pick the right structure. I have to pick hardware with the correct reliability. I need to know how many cycles my machine's running, because I need to determine, is this valve going to last long enough? And all of the manufacturers of safety products should have either a PFHD, an MTTFD, or a B10D value posted. If they don't have it, run, because it's going to be hard for you to do your safety calculations, which is what this is. That safety calculation uses number of operations per year and the B10D value. So the number of operations times 0.1 is divided into the B10D value to give you the failure rate. So it says your first failure would happen in 289 years. That's your first dangerous failure. And when I take that value, 289 years for that valve, 398 for the controller, and it was 300 for the light curtains, and I do my calculation, it comes out to 93-year reliability. It'd be 93 years before I'd have my first dangerous failure. And that tells me that's high reliability. Well, guess what? We're going to use that same MTTFD information along with something called diagnostic coverage, and that is basically depends on where you're putting your monitoring switches. Remember, you and I were talking about pressure switches. Depending on where you put it, you could claim anywhere from 0 to 99, depending on where you put it. And so looking at your circuits and choosing the correct diagnostic coverage then is important. So I've had people do this and say, I'm going to use 2 valves and I'm going to use 2 pressure switches. And I said, okay, well, you're not going to do it. You're not going to get to high diagnostics. Here's why. When the valves are off, the pressure switches say they're off. When the valves are on, air is being supplied, both pressure switches are on. If I turn those valves off and one of them sticks, guess what? As soon as this one goes low, both pressure switches go off, don't they? Did I detect that I have a stuck valve? No. That's what people are doing every day, and they're saying, I got 99% diagnostic coverage. They've really only got 60. And so they do their calculations wrong, and they end up with the wrong diagnostic coverage. So it should be low diagnostic coverage, not high. So they calculated it wrong. And then what that means then is they calculated it wrong. They said, okay, I had high diagnostics was 99. They actually had low. And if we're low diagnostic coverage with a Cat 3 structure, if I was trying to meet PLE, I'm not there. I'm only at performance level D. So calculating your actual performance level is an important thing. Most people don't even do that. And then there's a software called Systema that can help you with that. Well, guess what? There's a whole nother step. After you have done your design verification, you have to validate it. And that means you have to have a documented test plan of your machine. That documented test plan will go into your technical file so you can CE mark your machine. Most people do a terrible job at doing a validation. And it says that there shall be The validation plan shall identify and describe the requirements for carrying out the validation process. Validation plans shall also identify the means to be employed, and it shall validate that it meets the right categories and performance levels. So you should have what those specs are, what the test conditions are going to be, what the results of those tests are, and who's going to do them. And it's got to be documented. And that's why we put validation documents for all of our valves to help our customers. The process world is different. They use these different structures like voting. And I'm not going to go through all of these, but basically I've got 3 signals. One of them fails, the other 2 keep control of the process. There's different structures depending on what SIL level you have to meet. I'll just leave it at that because I know we're running over. And you have to evaluate your basic process control system. And then above the basic process control system is your safety instrumented system. Think of it this way. If this fails, this one's going to keep control. This is your safety backup. And that's really the big differences between machine safety and process. And that's why we developed a guidebook to help guide people through the whole design process. And that's why we created integration guides for all of our safety products. It tells you how to plumb it, how to wire it, how to program it, and how to test it. And so that's for every one of our safety products. And with that said, I'm 2 minutes over, so I'm sorry. Any questions? Any questions at all? Okay, we're good. Thank you all. Have a wonderful afternoon.
Thank you.